You know how a graph can sometimes feel like the ultimate mic drop, like that toothpaste ad
Yeah.
or a politician showing some chart?
Promising huge growth or whatever.
Exactly. And we tend to just see it as objective truth, right? Black lines, white background, numbers don't lie, supposedly.
But the way those numbers get presented, that can be, well, let's just say pretty twisted sometimes.
Okay, so that's what we're digging into today.
That's absolutely the plan. We're doing a deep dive into how graphs, how data can sometimes pull the wool over our eyes.
And more importantly, how you listening can get sharper at spotting it, become a more informed consumer of, well, everything you see.
Right. And we've pulled together some really, I think, insightful sources for this. We're looking at, spotting misleading graphs specifically, but also the bigger picture.
Like what?
Well, things like what even is data science, the whole peer review thing in science, why that matters for reliability, how science gets communicated or miscommunicated, and even some like basic stats concepts.
Gotcha. So the mission for this deep dive, it's pretty straightforward then. We want to arm people with practical knowledge.
Exactly. So you can look at data, look at a graph, whatever crosses your path, and really understand what it's showing you.
Or what it might be hiding.
Or what it might be hiding, yeah. And we want to do it without drowning everyone in jargon, just aiming for those, aha moments.
Love it. Seen The Matrix?
Kind of. Okay, so let's jump right in. Misleading graphs, those visual culprits.
All right.
We've got that great TED Ed video by Leah Gaslowitz. She highlights some classic tricks, and maybe the biggest one is messing with the y-axis, the scale.
Oh, yeah, the Chevy truck ad from '92. That's like the poster child for this, isn't it?
It really is.
The graph makes Chevy look way more reliable than Toyota. The bar's like twice as high.
But when you look closely.
Right, the actual numbers. It's like 98% reliable versus maybe 96.5%. Tiny difference.
But the graph starts at 95%.
Exactly. It only goes from 95 to 100, so you zoom away.
Put that on a proper 0 to 100 scale, and suddenly
the bars look almost the same height. It's crazy how much difference that makes visually.
It really messes with how we perceive it. We see a big visual gap, we assume a big real-world gap.
So, rule number 1, check the axis, always. Especially that vertical one.
Definitely. A zoomed-in scale can make tiny differences look enormous. And it's not just bar graphs either.
Line graphs, too.
Oh, yeah. Especially how they handle time on the x-axis. That can be sneaky.
Okay, like the unemployment chart example in the video from, 2008 to 2010?
That's the one. The timeline gets all squished. The 15 months after March 2009 take up way less space on the graph than the 6 months before it.
Ah, so it visually downplays how long things were still, well, not great.
Precisely. It makes the later period of job loss look shorter and maybe less severe than it was. Plot those exact same points on a consistent timescale.
And you see a much steadier picture. Okay, that makes sense.
And this ties right into cherry picking, which Gaslowitz also brings up.
Right, where you just pick the data points or the time range that makes your case look good.
You got it. You choose a very specific window to support your story, and you conveniently ignore the bits that don't fit.
Like starting that unemployment graph right after a huge financial crash. Of course, it's going to look like things are maybe starting to slightly improve eventually, but you miss the lead up.
Exactly. You crop out the foothills, just show the peak. It paints a very selective picture.
And it's not just start and end dates, is it? You can pick specific points within the graph, too.
Yeah, you could maybe smooth things over, hide some uncomfortable dips or spikes that happened in between the points you choose to show.
Okay, so we've got dodgy axes, dodgy timelines, cherry-picking ranges. What else? Missing information.
That's a huge one. What isn't being shown? The Super Bowl viewership example is perfect for this.
Ah, right. The raw number of viewers keeps going up year after year.
Makes it look like it's getting massively more popular, right? Exponential growth.
Yeah.
But when you factor in population growth, look at the percentage of people watching, the actual ratings.
It's basically stayed pretty flat for a long time.
Exactly. Leaving out that context. Totally misleading impression.
And sometimes the graph itself can be technically accurate, but we, the viewers, just don't grasp the significance. Like the ocean temperature graphs.
Right, using the same data. One graph shows the average annual temperature since 1880. It looks like a pretty gradual rise overall.
Yeah, it doesn't look that dramatic. Maybe a half a degree Celsius over a century or so.
But even that seemingly small average rise, ecologically, that can cause massive disruption.
Okay. So the significance is lost in just looking at the average trend line.
Precisely. That's why the second graph she shows, the one plotting the average variation each year, that's much more revealing.
Because it shows the increasing instability. More extreme highs and lows.
Yes, it shows that even a small average increase is linked to more frequent, more damaging extreme events. So the lesson for you, the listener,
Yeah.
you got to look beyond just the first glance.
Okay, so mental checklist time. When you see a graph, check labels, check numbers, check both axes. What's the scale? Does it start at 0? Is it zoomed in?
And what's the context? What's the bigger picture? What story are they trying to tell you with this visual?
And maybe, what are they not telling you? What's missing?
Excellent points. Okay, so moving beyond just the visual tricks, let's think about the actual data underneath it all. The world of data science.
Right. We looked at that Intro to Data Science video by Steve Brunton.
Yeah, and he really emphasizes that data science starts with asking questions. Questions you can actually answer with data.
And it's way more involved than just, running some numbers through a program, isn't it? Brunton lays out this whole life cycle.
It is complex. It starts with gathering the data, maybe from lots of different places, then storing it properly, and then this is a huge part, cleaning it.
Cleaning, like digitally dusting.
Sort of.
Huh?
Real-world data is messy, apparently, full of errors, gaps, inconsistencies.
But like detective work.
A bit, yeah, you have to wrangle it into shape. And this initial stage, collecting and cleaning, is critical.
Because if the data you start with is bad.
Garbage in, garbage out, right? If that cleaning isn't done well, or if there's bias in how data was collected or what's missing, then any graph you make later is built on shaky foundations. It could be totally misleading, even if the visualization itself looks okay.
Makes perfect sense. Okay, so after cleaning comes processing, visualizing, analyzing, modeling.
Right, and Brunton highlights visualization not just as like making pretty pictures, but as a core part of understanding the data, seeing patterns, and then communicating those findings.
Which brings us right back to how powerful visuals are and how they can be misused if the underlying work isn't solid.
Exactly. And Brunton also stresses that data science isn't just about data or algorithms, it's about people. Yeah. Solving problem.
Collaboration, right. He mentioned needing diverse teams.
Yeah, and he talked about needing more pie-shaped people.
Pie shape.
Meaning people who have deep expertise in a specific field like biology or finance or whatever, and also strong data science skills, not just one or the other.
Okay. So you need both the subject knowledge and the data skills. You can't just have a data whiz who doesn't understand the context of the data they're analyzing.
Precisely. And he also mentioned reproducibility. That's key in science generally, right?
Yeah, being able to get the same results again if you repeat the experiment or analysis.
If you can't reproduce the findings, how much trust can you really put in the data or any graphs based on it?
Good point. Reliability is crucial.
Which leads us neatly into how science maintains that reliability, especially in published research. And that's through peer review.
Okay, peer review. We hear that term thrown around a lot, like it's the gold standard.
It's definitely a cornerstone.
Yeah.
We looked at Jerry Vandenberg's lecture with Dr. Kyle Larson and also the scientific communication text. They give a good look behind the curtain.
So how does it actually work? A scientist writes a paper. Then what?
Okay, so you submit it to a journal. First, there's like a basic check. Are the files, okay, can they read it? Then it goes to the main editor.
And the editor reads it.
Usually, the main editor assigns it to an associate editor, someone who has expertise closer to the paper's topic. There's often a whole board of these associate editors.
Okay, so the associate editor is the gatekeeper.
In a way, yeah, because they make the first big call. Does this paper even go out for review, or is it rejected right away?
Really? They can just say no without sending it to other experts.
Absolutely. If they think the quality isn't there, maybe the research isn't rigorous enough, or maybe it's just not a good fit for that specific journal's audience, they can reject it. It's called a desk reject.
Wow. So just getting past the editor is a hurdle.
It is. Dr. Larson really recommended getting colleagues to read your paper before you even submit it. Get feedback early. It helps.
Makes sense. Okay, so if it passes the editor, then it goes out for review.
Typically, yeah.
Yeah.
Usually sent to 2 or 3 external experts in that specific field.
And who picks these reviewers?
The associate editor does. But often, the authors submitting the paper get to suggest potential reviewers, people they think are qualified.
Can they also say who they don't want, like rivals?
Yes, absolutely. You can suggest reviewers, and you can also list people you think shouldn't review it, maybe due to a conflict of interest, and you usually have to explain why.
Okay. And this review process, it's blind, right?
Usually single blind, meaning the reviewers know who the authors are, but the authors don't know who the reviewers are.
To encourage honesty.
That's the idea. Though Dr. Larson mentioned he often signs his reviews, standing by his comments, but the default is often anonymous for the reviewer.
Finding these reviewers sounds like it could be tough. Dr. Larson mentioned it's voluntary work.
It is. It's seen as a service to the scientific community. They don't get paid. So yeah, finding willing experts with the right knowledge and the time to do a thorough job, that can be a real bottleneck. Takes time. Editors often have to chase people down.
Okay, so the reviews come back. What kind of feedback do they give?
It varies a lot. It could be detailed comments embedded in the paper, maybe a separate report, emails. Basically pointing out strengths, weaknesses, suggesting changes, asking for clarifications.
And then the associate editor looks at all that.
Yep. They read the reviews, read the paper carefully themselves, and then they synthesize it all into a recommendation for the authors. Could be accept as is, which is rare, or minor revisions, major revisions, or reject.
And if it's revisions, the authors get a chance to respond.
Oh, yeah. That's crucial. They have to go through point by point, explaining how they've addressed each comment in the revised paper.
What if they disagree with a reviewer?
They can. They don't have to agree with everything, but they need to provide a clear, respectful, scientific justification for why they disagree. It's like a dialogue.
Okay, so they revise, send it back, then what? Decision time.
Back to the associate editor, yeah. They look at the revisions, the responses, and make the call. Still could be rejection, or maybe acceptance, or sometimes another round of revisions. Dr. Larson noted it's becoming more common to send revised papers back to the reviewers again.
Wow, sounds pretty rigorous.
It aims to be, though it's not foolproof, obviously. And Dr. Larson also mentioned alternative models, like open peer review, where the reviews and responses are published alongside the paper.
For more transparency.
Exactly. You can see the whole process, the discussion that happened. It helps understand the nuances.
Interesting. So peer review is this whole complex process to try and ensure scientific quality.
Right. But even good science that's past peer review, can still be communicated poorly or misinterpreted by the public.
Which brings us to effective science communication. Joe Filshie Browning's TEDx talk and that other text on the complexities.
Yeah, the pill scare story she told was really powerful, wasn't it?
It was chilling. A misinterpretation of risk, a small increased risk of blood clots from one contraceptive pill leading to widespread panic.
And then a jump in unplanned pregnancies and abortions. Real consequences for real people, all stemming from how the science was communicated.
It really highlights the stakes. So she had this checklist for better communication.
Yeah.
What were the key points?
Okay, first, talk about people, not just numbers. Make it relatable.
Like her dad explaining the blood clot risk in terms she could understand personally.
Exactly. Numbers alone can be cold, abstract, easy to misinterpret. Relating it to human experience, or even showing the scientist's emotions, like with the Higgs boson discovery. Yeah. That connects better.
Okay, people, not just numbers. What else?
Start with a headline. Get the main point across immediately.
Like her dad saying, don't stop taking the pill right away.
Right. Unlike a scientific paper that builds up slowly. Background, methods, results.
Yeah.
You need to grab attention in today's world. Bottom line up front.
So if you have a new Alzheimer's treatment, lead with that. Potential breakthrough in slowing Alzheimer's.
Yes. Don't bury the lead under layers of methodology.
Makes sense. And the third point?
Focus on what the science can do, its relevance, its potential impact, not just the nitty-gritty of how it was done.
So less about the complex gene sequencing, more about this could lead to earlier cancer diagnosis.
You got it. Make the so what really clear.
Okay, those are practical tips. But the complexities text suggests it's, well, more complex than just that, right?
Definitely. It's not just translating jargon. You have to think about your goals, the specific content, the format you use, and crucially, your audience.
Their existing knowledge, what they already believe, their values.
All of that. And communicating uncertainty, that's a big challenge.
Yeah, how do you talk about probabilities or margins of error without confusing people or making the science sound weak?
It's tricky. The text says unclear communication about uncertainty can lead people to think the science itself is flawed, or they might just lose trust. Transparency is key. Maybe using numbers and clear words to explain the level of confidence.
And people's comfort with numbers varies wildly too, right? Numeracy levels.
Hugely.
Yeah.
So strategies include just providing the info clearly, reducing the mental effort needed, explaining what the numbers mean in context, and really highlighting the key figures.
And we all have these existing mental models about how the world works.
Right. And they can be hard to change, even with good evidence. We also use mental shortcuts, heuristics, to make quick judgments.
And those shortcuts can bias how we interpret science, especially uncertain science.
They can. Emotions play a role, too. And motivated reasoning, seeing what we want to see.
Hmm.
And people with lower numeracy might rely more on these shortcuts or on simple stories.
So, like, if a study confirms something you suspected, you might just believe it without really checking the
That
details.
could be an example of motivated reasoning or confirmation bias, yeah.
And framing matters too, how you present the same information.
Yeah, like emphasizing gains versus losses or highlighting certain aspects. The evidence is a bit mixed on how effective different frames are, but it's definitely something communicators think about.
And all this applies to policymakers too. They're not immune to values and shortcuts.
Not at all. Building trust through sustained interaction between scientists and policymakers is really important there.
And trust itself is key across the board. Integrity, competence.
Absolutely.
Yeah.
Trust influences if people even pay attention, if they believe the findings, if they support science-related decisions. And timing matters too.
Yeah.
Reaching people early, maybe before strong opinions form. Sometimes you need long-term communication efforts.
But even with good intentions, there's this problem of overhyping science, right? That Veritasium video hit this hard.
Oh, yeah. The holographic wormhole example was classic.
Headlines screaming, "Scientists create wormhole," when it was a mathematical simulation on a quantum computer.
Basically, yeah, a theoretical representation, not a physical wormhole you could, travel through. Total misrepresentation fueled by hype.
And the video points to bad incentives all around. Scientists needing funding and attention.
Universities wanting good PR, press releases, simplifying things too much.
Journalists needing clicks.
It creates this environment where surprising, unexpected results, even if they're more likely to be wrong, get amplified.
Derek Miller, the host, mentioned his own experience with the BIICEA P2 results, the supposed gravitational waves that turned out to be dust.
Right, and his point was crucial. Initial reports of huge breakthroughs are often wrong. Need that skepticism.
Like the recent room temperature superconductor claims. Huge buzz, but the actual data didn't really hold up under scrutiny.
Exactly. Didn't show zero resistance consistently, weird magnetic behavior. It didn't match the hype, but the story flew around the world.
And the corrections or retractions, they never get the same attention, do they?
Sadly, no. The lie gets halfway around the world. You know the saying.
So this hype gives people a skewed idea of science, like it's just a constant earth-shattering breakthroughs.
Yeah, and it can erode trust when those breakthroughs fizzle out. It happens with whole fields, too, like fusion sometimes. Decades of slow progress get overshadowed by hype about the next big thing being just around the corner.
Veritasium also distinguished between established science and speculation, right? Like string theory being presented as fact sometimes.
Yeah, the media can blur those lines. He basically argues that while hype might bring short-term attention.
It's the solid, tested, validated science that actually lasts.
Exactly. So, as consumers of science news, we need to be aware of those incentives, be extra skeptical of amazing, surprising results, especially if they haven't been independently replicated.
Got it. Healthy skepticism is key. Okay, finally, to really understand the data behind the graphs and the headlines, a little bit of statistics helps.
Immensely helpful. That basic statistics document laid out some fundamentals.
Let's touch on the basics. Central tendency, like the middle of the data.
Right. You've got the mean, that's the average, just add everything up and divide. But be careful, it's sensitive to outliers, those extreme values.
Okay, what else?
A median. That's the actual middle value when you line all the data points up in order. Much less affected by outliers.
And the mode.
That's simply the value that shows up most often. Useful for certain types of data.
Okay, so mean, median, mode. Tell us about the center. What about how spread out the data is? Dispersion.
Good question. The simplest measure is the range, just the difference between the highest and lowest value. Gives you a quick idea, but again, sensitive to outliers.
So what's better?
Variance and standard deviation. They measure, on average, how far each data point is from the mean.
Variance, standard deviation. Aren't they related?
Yep, standard deviation is just the square root of the variance. The nice thing about standard deviations is it's in the same units as your original data.
Okay, so it's easier to interpret. Like, a standard deviation of 5 kilograms makes more immediate sense than a variance of 25 kilograms squared.
Exactly. It gives you a typical amount of spread around the average. Small standard deviation means data points are clustered close together. Large means they're more spread out.
And it helps spot outliers, too.
Yeah, there's a rule of thumb for normal distributions data points. More than, say, 3 standard deviations away from the mean are often considered potential outliers. Worth investigating.
So understanding these basic stats, mean, median, standard deviation, really gives you more power to interpret data critically.
Absolutely. You could look beyond the headline number or the simple graph and ask, okay, but what's the spread? Are there outliers influencing the average? It adds another layer of critical assessment.
Okay, fantastic. So let's try and wrap this deep dive up. Key takeaways.
Well, definitely be critical of graph scales and axes. Don't let a zoomed-in view fool you.
Always think about what might be missing data points, context.
Understand the incentives behind science communication. Why might something be getting hyped?
Remember, peer review is important, but it's a human process, not infallible.
Recognize our own mental shortcuts, how framing affects us. Be aware of those biases.
And yeah, getting a handle on basic stats, mean, median, standard deviation, gives you real tools to question the data presented to you.
So hopefully you, the listener, feel a bit more equipped now, more savvy.
Definitely. So maybe the final thought to leave people with.
How about this? The next time you see a really compelling graph or read a science headline that seems almost too good to be true, pause. Ask those questions.
Check the axes. Think about the context. Consider the source.
Exactly. True understanding doesn't come from just accepting what you're shown. It comes from questioning, from digging a bit deeper, even when something looks like objective data.
Because data always has a story behind it.
And sometimes that story is trying really hard to convince you of something specific. It pays to be discerning. We really encourage everyone to explore these ideas further.